Let's begin with question 4.4. Now the thing that looks a bit intimidating about this is the angle at which the channel is shown. But you don't need to stress about it too much. It's actually quite simple to deal with. And once you get a hold of that, the rest of the question is quite simple. So as usual, we will begin by assuming that the fluid is incompressible. Remember, water is mostly incompressible. So we're just going to write here, assume water as incompressible. Now the reason we do this is because if water is incompressible, then as water goes through the tube, it cannot compress so that more mass enters than exits. Every piece of mass that is entering must exit, and that way you are, by implication, operating at steady state. Okay, and steady state makes it easy for us because steady state means that in our continuity equation, which I write out, therefore, the thing about steady state is that if I am at steady state, I have no change with respect to time, and this entire term can disappear. And now you only have to fill this in. So that's done. Now that we are done with that, let's select our control volume. So the channel looks a bit like this, with a straight entrance and a crooked exit. All right? Now you want to fill in your, it's not very neat. I tried my best. Okay, now you want to fill in your normal and your velocity vectors. So remember, your normal vector always points perpendicular to the control surface and away from the control surface. So perpendicular to and away from the control surface is normal 1. The velocity, the fluid is entering, so velocity is in this direction. On the exit side, however, they tell you that the mean velocity of the discharging water remains horizontal. So that means that the velocity will still be this way despite the angle. Now, however, remember that your normal vector is always perpendicular to and away from the surface of the control volume. So it's actually going to go out like this. Now remember, if this was a perfectly straight tube, then we are hanging 30 degrees off of the normal. So if my surface tilts 30 degrees, then my perpendicular also tilts 30 degrees. So this perpendicular is now 30 degrees from the V2. And I'm going to label that N2. Okay, then you should always just put in a dotted line to indicate what your control volume is. And I'm just selecting the control volume a little bit to the inside, just before the walls of the channel. Okay, so we have our control volume, we have our normal vector, velocity vectors, everything is done. Let's begin filling in some variables now. So we're going to do everything symbolically in variables, and as the last step, start substituting numbers. So let's begin. Our double integral over the controlled surface, rho v n dA, is equal to the density of the fluid multiplied by velocity 1 multiplied by normal 1. So if you ever need help turning a normal vector into a number, remember that the normal represents the angle between the velocity vector and the normal vector. So here's velocity vector 1, here is normal vector 1, and the angle between them, 180 degrees. So to turn that into a number, you simply say cos of 180 degrees, and that's it, you're done. Then you multiply by area 1 plus, again, density of the fluid, velocity 2, normal vector 2. Now, don't get stuck. The normal vector, this angle is simply cos of the angle between the normal vector and the velocity vector. So if I can just redraw it here, we have our velocity vector and we have our normal vector. To turn this N2 into a number, you simply say the angle between the velocity vector and the normal vector is 30 degrees, so I'm going to put cos of 30 degrees. Then you might say to me, okay, how do I know whether it's minus 30 or plus 30? Remember, cos of negative theta equals cos of theta. It doesn't matter whether you put the negative or the positive, you will still get the same answer on the calculator. So don't stress about it. All right? So we filled in our normal, and now we need to multiply by area 2. Okay. Next. This is equal to 0. All right? Let's start by moving this over to the other side, because remember, this cos of 180 becomes minus 1. Cos of 30 degrees is a positive number. So let's begin. Rho V1 multiplied by A1 Okay, I moved it over to the other side, is equal to rho V2 cos of 30 degrees multiplied by A2. All right, we can cancel the densities because we're talking about the same density of the same fluid. All right, now we've got V1 and V2. So you need to ask yourself, what are we looking for? We want to find the exiting water's average velocity and total flow rate. We'll discuss the flow rate just now. Let's find the exiting velocity V2. So we want to solve this equation for V2. So V2 is equal to V1 times A1 divided by A2. This whole thing is multiplied by cos of 30 degrees. All right, so we've got this going for us. Let's start substituting in numbers. So V2 is equal to V1, 10 foot per second multiplied by area 1. Now remember, area 1 is in inches. So to convert inches to feet, you need 12 inches to make 1 foot. So you have 4 inches divided by 12 multiplied by 4 inches divided by 12. And that's because you have 4 inches multiplied by 4 inches to give you the opening area, 4 by 4. Okay, and I've divided by 12. Then I'm going to divide by area 2. Area 2 is 2 inches. So I'm going to divide by 12 and multiply it 2 over 12. That's because area is equal to length times length. All right, and then cos of 30 degrees. So we can put this all into our calculator now and get a nice answer. And we end up with 46.19 foot per second. All right, and that is our velocity. The next thing they ask us for is the total flow rate. So remember, rate implies per second value, something divided by seconds, okay? Now, when they say flow rate, remember you can have a mass flow rate, or you can have a molar flow rate, or you can have a volumetric flow rate. So all of this means mass flow rate means kilogram per second, mole per second, and meter cube per second. So in this case, we're going to assume they are referring to a volumetric flow rate and give them the volumetric flow rate. So if this is 46.19 foot per second, then you need to remember that V with a dot is usually the symbol that we use for volumetric flow rate. The dot indicates with respect to time. It indicates a rate. Okay, so volumetric flow rate is equal to velocity multiplied by area. And because it's exiting flow rate, we are dealing with area 2 and velocity 2. So we already know the velocity 2, we already know the area 2, so we can work out the volumetric flow rate. So velocity 2 is 46.19 foot per second multiplied by area 2, which is 2 over 12 multiplied by 2 over 12. And that should give me 1.28 cubic foot per second. And there we go. I hope that makes sense. I hope this was helpful.